We begin with chapter 1 on the free vibrations of single degree of freedom systems, SDOF in short. The chapter here in this set of slides contains 3 sections. I will be adding one more section on the response of viscously damped systems later, but in this chapter here, in this set of slides, we are going to look at the response of undamped systems using D'Alembert's principle or Newton's second law of motion. And then we're going to look at the same systems using the conservation of energy principle in section 2. Section 3 contains a partial set of problems because I will be uploading more problems on undamped systems vibrating freely later on also. Okay. Response of undamped systems using D'Alembert's principle or Newton's second law of motion. What we would like to do in this section is to derive the equation of motion of a basic spring mass system and then solve the equation of motion to determine the response of such a system. We model the system as shown in figure 1.1.1a, where we have a mass which is taken to be a particle here. The size of the object here is immaterial. The mass is attached to a spring of stiffness K. The spring is unstretched and the mass rests on a frictionless support. Friction is neglected here. In the position shown, the system is at static equilibrium. And this position, the position of static equilibrium, is going to be considered as our reference, meaning our origin is set at the static equilibrium position. And since we need to decide which direction for the displacement is positive and which is negative, we decide that any displacement to the right of the equilibrium position is going to be positive and to the left is going to be negative. And the displacements are denoted by x here. Now, what we want to do next is disturb the equilibrium of the system and observe it oscillate horizontally and then analyze the mass as it is oscillating in the vertical plane here. In order to disturb the equilibrium, what we can do is pull the mass slightly to the right, or maybe push it slightly to the left, or impart to it an initial velocity, or do both, impart an initial velocity and an initial displacement, pull it to the right or push it to the left. We set it in motion, the mass starts oscillating, and I should mention at the outset that all displacements that we are going to consider are going to be small. We will only deal with small displacements so that our differential equations remain linear. When we disturb the equilibrium of the system and the mass is oscillating about the equilibrium position, we freeze the mass at some time t, and let's say at the time I froze the mass is or was at the right of the equilibrium position, at the right of the origin. We draw the free body diagram of the mass, and the forces acting on the mass are its weight, mg, acting down, the reaction from the support N acting up, the force from the spring on the mass kx acting to the left towards the origin, towards the equilibrium position, and a force which I also show acting opposite to the motion. Motion is to the right, opposite to the motion is to the left, and that is equal to mx double dot. Now, mx double dot is not a real force, but if you use D'Alembert's principle considers that the inertia term is a force, although it's not a force. But if you look at it as just another force that is added to the real forces, then you can sum all the forces acting on the mass and set the sum equal to 0. This way you would attain dynamic equilibrium. Of course, if you choose to use Newton's approach, Newton's second law of motion, sum of forces equal to ma, then you would arrive at the same result. The two methods are equivalent. I prefer to use D'Alembert's principle because I think it's simpler, particularly when you're looking at more complex problems than what we have here at hand. So you sum the forces and you obtain an equation of the form mx double dot plus kx equals 0. This equation is called the equation of motion of the system, the EOM of the system. It is a linear, second-order, homogeneous, ordinary differential equation with constant coefficients, whose solution, this can be looked up in any book on ordinary differential equations, a textbook, typical textbook would have this. X of t equals k1 cosine omega nt plus k2 sine omega nt. X of t is called the free response of the system, and it gives the position or displacement of mass m as a function of time, t. Furthermore, the response is said to be free because the system is not subjected to any externally applied force. In other words, the mass is allowed to oscillate under its own inertia, and not because it is under any externally applied load. K1 and K2 are constants which are determined from initial conditions. The initial conditions would be set on displacement and velocity, as we will see later. Omega n is equal to square root of k over m. This is an important quantity called the natural frequency, or the natural angular frequency, or also the circular frequency of the system. I like the term natural frequency. What is the natural frequency? It is a measure of how fast the oscillations repeat themselves. This is kind of similar to velocity, except here it measures the rate of repetitiveness of the oscillations. Common units for omega n are radians per second or hertz. 1 hertz is 1 cycle per second. There's a relation between radians per second and hertz. If Fn is in hertz and omega n is in radians per second, then omega n is 2 pi Fn. Finally, the period of oscillations, commonly expressed in seconds, is capital T equals 2 pi over omega n. What is the period? The period is simply the time it takes for the oscillations to repeat themselves. As we said, initial conditions on displacement and velocity may be imposed as follows. X at t equals 0 equals x naught. This is the initial displacement, and x dot at t equals 0 equals x naught dot, or v naught. That's the initial velocity. Now, using the initial conditions, the response becomes x of t equals x naught cosine omega nt plus v naught over omega n sine omega nt. Now you can see that the response has a cosine and a sine term in it. Sometimes it's more convenient to express the response in terms of just one sine or one cosine. with the help of known trigonometric identities. In this case, I can rewrite 1.1.4 as 1.1.5, which has the form x of t equals a sine omega nt plus phi. Now, this way I have the response in terms of one sine function because it's easy to visualize the behavior of the sine function or the cosine function. The coefficient here of the sine, which is a, is equal to square root of v naught squared plus x naught squared omega n squared over omega n. That's called the amplitude. And phi right here, which is tan inverse x naught omega n over v naught, is called the phase shift. The amplitude and the response, of course, have units of displacement, and the phase shift is in radians. Now, it should be emphasized that by displacements, we may mean distance or angles. In this case, since we have a translational system, the mass is oscillating with respect to the origin, left and right of the origin. The displacements are distances, therefore. But if we had a rotational system or a torsional system, then the displacements would be angles. Equation 1.1.5 describes what is called simple harmonic motion, and in fact the model in figure 1.1.1 is referred to as an harmonic oscillator or as an undamped single degree of freedom system vibrating freely. We say undamped because no damping device is present to extract energy from the system. Some examples of harmonic functions are discussed next to show you how one function may be formed from the basic harmonic function. Figure 1.1.2a depicts the graph of the simplest harmonic function x equals sine t, or I could have used cosine t. Here, of course, a is 1 millimeter, omega n is 1 radian per second, and phi equals 0. Figure 1.1.2b shows the graph of x of t equals sine 2t, where the amplitude is still 1 millimeter, but now the frequency is 2 radians per second, and phi is still 0. Part A of the figure shows the graph of the basic sine function, sine t, of period 2 pi. Part B of the figure shows the graph of sine 2t, and you can see that the period has decreased to pi, which means that the oscillations are faster. And you can also see that sine 2t, the graph of sine 2t, is obtained from the graph of sine t by compressing the graph by a factor of 2 along the t-axis horizontally. Compression of the graph of sine t to obtain sine 2t is due to the fact that omega n is greater than 1. It is equal to 2. Had we had an omega n less than 1, then we would have an expansion, horizontal expansion of sine t rather than a compression. Figure 1.1.2c shows the graph of x of t equals sine 2t minus 1. We have the same amplitude, the same frequency of 2 radians per second, but now phi is minus 1 radian. Now, if we let 2z be 2t minus 1, then the graph of sine 2z has the same appearance as the graph of sine 2t, or sine 2u or sine 2y. The variable is just a dummy variable. So if 2z is 2t minus 1, then t is z plus 1/2. What this tells us is that the graph of x of t equals sine 2t minus 1 is obtained from x of t equals sine 2t by shifting the entire graph of sine 2t horizontally to the right by 1/2, or by absolute value of phi over omega n. Finally, part D of the figure shows the graph of x of t equals 0.5 sine 2t minus 1, where now here the amplitude is 0.5 millimeter, omega n is still at 2 radians per second, and phi at -1 radian. This is obtained from x of t equals sine 2t minus 1 by simply multiplying the x coordinate of every point of sine 2t minus 1 by 0.5. This is now section 1.2 on the response of undamped systems using the conservation of energy principle. The equation of motion, equation 1.1.1, may be derived using the principle of conservation of energy, which says that the total energy in a conservative system remains unchanged when the system moves from an initial state to a final state. Thus, if T represents the total kinetic energy in the system, U the total potential energy, and C is some constant, then conservation of energy requires that T plus U be equal to C. For the system shown in figure 1.1.1, setting the datum at the position of static equilibrium, we have T equals 1/2 mx dot squared, that's your familiar 1/2 mv squared, and U equals 1/2 kx squared. The total potential energy in the system is due to the energy stored in the spring. Thus, T plus U equals a constant means that 1/2 mx dot squared plus 1/2 kx squared equals C. Now differentiating both sides of this expression with respect to time yields mx dot x double dot plus kx dot x equals 0. And finally, dropping x dot, we obtain the same equation of motion as 1.1.1. Let's look now at some problems from section 1.3. And as I mentioned before, more problems are going to be uploaded in a different set of slides later that pertain to undamped systems. I will also add a section on damped free systems along with problems, again in a different set of slides. Let's start with the first problem. And by the way, the figure numbering and the equation numbering in problems are going to be a little bit different than those in the notes. The first digit in the figure numbering refers to the problem number. So figure 1.1 means the figure, the first digit here, the figure 1 is for problem number 1, and then the second digit refers to the number of the figure. Prove that the equation of motion of the spring mass system in figure 1.1 right here is the same whether the system oscillates horizontally or vertically under the action of gravity. Gravity acts down in this case. So what we have is again the spring mass system hung vertically now, and when the mass is attached to the spring, it deflects the spring a distance delta s, which we will call delta static, and then the system attains static equilibrium. This is going to be our reference again, so we will set our origin at the static equilibrium position, and then we'll set the system in motion. So figure 1.1a shows the system hung vertically under the action of gravity, as we said. When the mass is first attached to the unstretched spring, it deflects the spring distance delta S before the system attains static equilibrium. Thus, delta S is the static deflection of the spring, and it defines the static equilibrium position of the system. All subsequent displacements are measured from the static equilibrium position. Now, if we draw the free body diagram of the mass at rest at the static equilibrium position, then of course mg is equal to k delta S. The system is then set in motion. For example, I can pull down a little bit on the mass and let go. The mass starts oscillating up and down about the static equilibrium position. So the system is set in motion, and the free body diagram of the mass is drawn at some time t, when the mass is moving down by x, as shown in figure 1.1b. So this is when I freeze the system. I freeze it at the time when the mass is at some x below the datum, below the static equilibrium position. We have the forces acting on the mass, which are the weight mg, the reaction from the spring k times delta S plus x, and of course, using D'Alembert's principle, I have the inertia quote unquote force, which is not really a force, mx double dot, and this is shown acting upward on the mass because motion is down, the mass is going down. Therefore, by D'Alembert's principle, I will show mx double dot acting up, and I will choose the downward position, the downward direction as the positive direction when I sum forces. Therefore, summing forces on the mass, assuming the downward direction to be positive, we get minus mx double dot minus k times x plus delta S plus mg equals 0. Now equation 1.2 right here together with equation 1.1, because if I take k delta S here and put it in for mg, it will cancel out of the equation. So 1.2 together with 1.1 yield the same equation of motion as 1.1.1. Thus, by placing the origin at the static equilibrium position, and when the weight of the mass is balanced by the static deflection of the spring, equation 1.1 right here, the weight of the mass is balanced by the static deflection of the spring, we can eliminate mg and k delta S from the equation of motion. This is an important result, and this setting the origin at the static equilibrium position is always a good idea for a lot of the problems that we will be dealing with, if not all of them. Problem 1.3.2, derive an expression for the total potential energy in the system shown in figure 1.1, which is the system hung vertically. Let us plot the force in the spring of the system in figure 1.1 versus the spring displacement as shown in figure 2.1 right here. We're going to place the origin of the coordinates at O, which corresponds to the location of static equilibrium of the system in figure 1.1. Thus, at point O, the force in the spring is mg, which is point A in figure 2.1. So from here, from O to A, the magnitude is mg, which is equal to the force in the spring. And the displacement is 0 since O is our reference, it's our origin. This is the point from which subsequent displacements are going to be measured. So therefore at O the displacement is 0 but the force is mg. Now when motion starts, the mass is at some x with respect to O. The displacement is x, therefore from O to D is x. And the spring force is now equal to mg plus kx. So at point D, we have the deflection of the spring when the mass is at some x below the datum, and therefore the force there at B is mg plus kx. So the coordinates of point B in this graph are going to be x, comma, mg plus kx. Now, the potential energy in the spring is equal to the trapezoidal area under the force displacement curve. This is the force displacement curve AB, which is the sum of the areas of rectangle OACD and triangle ABC. I need this area, which is the area of a trapezoid, and I can break it into or split it into two areas. We have the area of the rectangle OACD and the area of the triangle ABC. If we add the two areas, we get the following total area, the area of the trapezoid below the straight line, mgx plus 1/2 kx plus mg minus mg times x equals mgx plus 1/2 kx squared. The potential energy of the mass is minus mgx, since the mass is at the distance x below the datum. This is the potential energy due to a change of height. The datum is the static equilibrium position, of course, at this instant of time. Therefore, the total potential energy in the system, that is the potential energy stored in the spring and the potential energy due to the difference in height of the mass, is equal to mgs plus 1/2 kx squared minus mgx, and we get back 1/2 kx squared. This result agrees, of course, with the system vibrating horizontally as it should be. Problem 1.3.4, prove analytically that the potential energy stored in the spring of the system in figure 1.1 is 1/2 kx squared plus mgx. Assume gravity acts down. I will let you read the solution. I think it's self-explanatory. We basically take a spring element and calculate the potential energy stored in the spring element, and then obtain the total potential energy stored in the spring by integrating over the length of the spring that has been deformed a distance x, deflected a distance x. So I'll skip over this problem. Problem number 5. Derive the equation of motion for the disk shown in figure 5.1a using both Newton's method or D'Alembert's principle and the conservation of energy principle. The disk has mass m and radius r and rolls without slipping on the surface right here. So we have, in addition to the disk, we have two springs, spring 1 and spring 2, which are attached to a point that is at a distance a from the center of the disk. The springs have stiffnesses K1 and K2 respectively. The system is at static equilibrium, the way it is shown here, and we're going to disturb the equilibrium of the system the usual way by, say, pulling or pushing to the right or to the left. We set the system in motion, or we can impart an initial velocity also to the system. This is a problem of a disk undergoing general plane motion, because when I disturb the equilibrium, the center of mass of the disk moves horizontally oscillates about the initial static equilibrium position, and at the same time the disk will rotate clockwise and counterclockwise. So therefore I have translation plus rotation. This defines plane motion. And suppose that during the oscillations of the disk I freeze the motion at an instant of time when the center O is displaced a small distance x to the right of the equilibrium position. And at the same time, I freeze the motion when the disk has rotated by a small clockwise angle theta. When this happens, then each spring is going to be stretched or compressed by the same amount u. Spring 1 would be stretched in amount u, and spring 2 would be compressed in amount u. Also, at that instant of time, the point of contact of the disk with the support is O prime, and you can see the disk in its current position. This is the contour in a solid line. The contour in dashed lines is the initial or equilibrium position of the disk. Here's the point of contact of the disk O prime with the surface. Solving the problem by the conservation of energy principle, T plus U equals a constant, or 1/2 mvo squared plus 1/2 IO theta dot squared, that's the total kinetic energy in the system, plus 1/2 K1 U squared plus 1/2 K2 U squared equals C. This is the total potential energy in the system. Now, the expression for the kinetic energy stems from the fact that the cylinder or disk undergoes plane motion. You have a translation of the center of mass of the disk and the rotation of the disk at the same time. Note that VO, the velocity of the centroid of the disk, is equal to VO prime plus VO with respect to O prime. That's the relative velocity formula. But VO prime is 0 because O prime is the instantaneous center of zero velocity. Recall that the instantaneous center of zero velocity is a point about which the entire body, in this case the entire disk, is rotating at that instant of time. And so you can imagine that there is a pin here at O prime, and the entire disk is rotating about that pin. So therefore VO prime is 0, and VO with respect to O prime, that's the velocity of O as observed from O prime. Since there is a pin here, the rotation is simply R times theta dot. And so we get VO to be R theta dot. Also, IO is 1/2 mr squared. That's a known formula for the mass moment of inertia of a disk or a cylinder about its center of mass. Now, substituting this and the expression for VO into equation 5.1, we get the total kinetic energy in the system to be equal to 1/2 times 3/2 mr squared theta dot squared. Now, if you look at 5.3, this is the same as 1/2 IO prime theta dot squared, because if you use the parallel axis theorem, then IO prime is IO plus mr squared. And IO prime, of course, O prime being the instantaneous center of zero velocity, this means that we could have considered that the disk is undergoing pure rotation about O prime. So I have the choice here. I can look at O, in which case the disk is undergoing rotation plus translation, or I could look at O prime, in which case the disk is undergoing pure rotation about O prime. Either way, the answer is of course the same. The displacement of each spring is U equals x plus a sine theta. X is of course the displacement of the center of mass, and a sine theta is the displacement of each end of the spring. But for small theta, sine theta is equal to theta, and so I get U to be equal to R plus A times theta. Therefore, the potential energy in the system is 1/2 times K1 plus K2 times R plus A squared theta squared. Now, from 5.3 and 5.4, the principle of conservation of energy requires that 3/2 mr squared theta double dot plus K1 plus K2 times R plus A squared theta dot theta equals 0 upon differentiating with respect to t. And finally, dropping theta dot, we get the equation of motion as shown here as equation 5.5. Now, choosing to solve the problem using D'Alembert's principle or Newton's second law of motion, it would be necessary to draw a free body diagram of the cylinder undergoing plane motion. Here we have the weight mg acting at the center of mass. I have a force from the left spring, from spring 1 on the cylinder acting to the left, from the right spring on the cylinder also acting to the left, K1U for the left spring, K2U for the right spring. I have the friction force FF, which I choose to have it act to the left. This is an arbitrary choice because FF as of yet is unknown, which means that I can simply assume its direction because I don't know it yet. N, which is the reaction from the support, acts up, and I'm also showing mx double dot, which again, according to D'Alembert's principle, is just another quote unquote force, although again, let me emphasize that this is not a real force. And this is acting opposite to the motion because motion is to the right here by x. Therefore, mx double dot is shown acting to the left at the center of mass. And in my mind, I would be summing moments about the instantaneous center of zero velocity O prime. Therefore, I show the inertia term due to rotation, I O prime theta double dot, acting again opposite to the motion. So motion is to the right for O and clockwise for the cylinder or the disk. Therefore, I will show an I O prime theta double dot acting counterclockwise at O prime. Now, summing moments about O prime and taking the clockwise sense as positive, we get minus I O prime theta double dot minus K1 plus K2 times U times R plus A equals 0. Now, of course, we've calculated I O prime and U before, and if you put in the numerical values of I O prime and U in this equation, you will obtain again equation 5.5. And that is the end of Newton's method applied to this problem. Of course, we could choose to sum moments about O rather than O prime. However, in this case, we would introduce the friction force FF, which is unknown, and would therefore need to sum forces in the horizontal direction in order to obtain a second equation. We would also need to use the relation x equals r theta, which holds true under no slip conditions. And in this way, we can derive the same EOM as found before. and this ends the lecture in this set of slides.